So this is the fourth video on module 3. Recall that last time I defined what are exact sequences and what are split exact sequences. So today we only need exact sequences. So a sequence of homomorphisms and modules, say from mi to mi plus 1 to this kind of where each mi is an R module and you have these module homomorphisms between them. This sequence is said to be exact if image of this fi coincides with kernel of fi plus 1. So if this happens, then we say this is exact at mi plus 1, and if this happens at every mi, then we call this sequence exact. Okay. So today I'm going to be talking about what is called the five lemma. So the lemma is two parts. Firstly, let me write the first part. So this is called the five lemma. So here you have two exact sequences of five modules each. So that is what's called the five lemma. So in the first row you have say A1 to A2, A3, A4 and A5. And in the second row you have B1 to B2, B3, B4 and B5. And in between call these maps say phi 1, phi 2, phi 3, phi 4 and here it is psi 1, psi 2, psi 3 and psi 4. Okay. And connecting these two exact sequences you have Fi in between from Ai to Bi for each I from 1 to 5. So in particular F1 here, F2, F3, F4 and F5. Okay, so the first part of this lemma is saying, and moreover each such squares like this square, this and this. So these four squares are commuting. That means if you go from A1, let me just write it in another color. So if you go from A1 to say A2 and then to B2, it is same as going from in this way to B1 and then to B2. So by this we mean the square is commuting, and this is true for each of the four squares. Okay, so now the first part of this lemma, it says that suppose you have suppose F1 is surjective, the this map, and moreover F2, F4 are 1. Then the map F3 is again 1. Then F3 is also 1. So, mm, write it clearly. So, yeah, F3 is also 1. So, let's see how to prove. So, let me just write this diagram again. So, you have this. Okay, so this is your diagram. And so, what we need to show that if 3 is 1, this is the map F3. So that is equivalent to show if is the kernel of this map is just the zero vector or the zero elements. So let's see. So let us pick an arbitrary element from the kernel of F3. So X is right here. Is in F3. Okay. And now there is only one way to go because if you apply F3 will go to 0, right? So that will not give you anything more. So you can go via phi 3, right? And this will land you inside F4. And if you apply now F4 to it, you will get 0, right? Because due to commutativity of this square, this is same as if you apply F3 first and psi 3 then. But F3 of x is 0 because x is coming from kernel of F3. Right? So this is um, So X was chosen from kernel of this map in between, the third map. Yeah. So now this is 0. But F4 is injective, right? And so phi 3 of X is in kernel of F4. But F4 was injective, so it is 0. And that means X belongs to kernel of phi 3. Right? But again, because this is an exact sequence, so this is same as image of phi 2, right? So you can lift X to a free image under this map phi 2. So I can call this element A2, where A2 is coming from capital A, right? So now you're here. So you need to take care of this diagram. You need to track where you are at the moment. So now from A2, you can go via F2, right? That will go land you inside B2. Okay. So let's see. Now we need to use all of these facts that if 4 is injective, I've already used. So next we have if 2 is injective and also that if 1 was surjective. Okay. So now you can go to via F2, you can go to B2. This will take you inside B2 and from say if you go to then you if you apply shy 2, this is shy 2 F2 of A2. This is again due to commutativity is same as F3 phi 2 of A2, but that is 0, right? Because X was this. So you will get F2 of A2 is in kernel of psi 2. But kernel of psi 2 is same as image of psi 1 due to exactness of this bottom row. And so you can lift F2 of A2 to a pre-image under psi 1. Let's just call it B1. So now you are here. But again, because B1 is from capital B1 and F1 was chosen to be surjective. So B1 must have a pre-image under F1. So just let's take any pre-image, call it A1. Okay. So now you get B1 is F1 of A1, right? Okay. So then, but that is psi 1. So here it is psi 1 composed with F1. But that is same as if you apply phi 1 first and then F2, right? Because this diagram is commutative. So this. And now this is clear because F2 was injective. So A2 must be equal to phi 1 of A1, right? Because here is F2 and here is also F2 due to injective. And then it is pretty much clear because then if you apply say phi 2 or psi 2, you will get 0, right? Because phi 2 composed phi 1 is 0 because this top sequence is exact. And, and that was your X. So you get kernel of F3 is the 0 module and hence F3 was F3 is 1. Okay. That is the first part. So what we did is we just used the fact that F1 was surjective and F2, F4 both are injective, and just some careful using of the fact that the squares are commutative and the rows are exact. So nothing more we have done actually. Okay, so let's come to the second part of this lemma, which is again kind of similar to the first part. Let me write it again. Okay, so here we have F2 and F4 was injective. So now suppose both are surjective. Suppose F2, F4 are on to, and moreover the rightmost map that is F5 is injective. Then it implies that the F3 is again on. Okay, so the proof will be kind of similar. So yeah, let's do it again. Let me just draw the diagram. So here you have A1 to A2, F3, F4, F5. Here you have B1 to B2 to B3 to B4 and B5, right? So this map F5 is injective, F4 is surjective, F3 we need to prove F2 was again in surjective, and if1 we don't need any information about F. And in between the maps are phi I between EIs and psi I between BIs. Okay. So now let's see how we can do. So take any element from B3, right? And we have to produce a pre-image of Y under this map F3 to show F3 is surjective. That is clear. And now, so you have this. And there is only one way to go from here, right? So you can apply psi 3 of Y, and that will land you inside B4. So now you're here at B4. Okay. And from here, because F4 and B4 was the image of F4, right? Because F4 was surjective. So you get psi 3 of Y has a pre-image under F4. Let's call it A4. So now you were right here. And then we can apply phi 4 to it. So to apply, if you apply phi 4 and then you apply F5, let's see what happens. So let me just apply phi 4 first. So phi 4, and here we have used that F4 was surjective. So we have used this one. So now if you apply phi 4 to F4, uh, you will go in say A5, and then you can again apply F5. But due to commutativity, this is same as if you apply F4 to it and then psi. F4, right? But F4 of F4 is psi 3 of Y, and we know psi 4 composed with psi 3 is always 0 because the bottom row was exact. So you get phi 4 of F4 is 0. This is due to the fact that F5 is injected. And so it implies A4 belongs to kernel of phi 4, but that is same as the image of phi 3. Again, the usual stuff. And so you can lift it to some element inside A3. Let's just call it small a. So you're at A3. So A4 is phi 3 of A3. But now, see, you are back at A3, but there is no reason to believe that this should be the pre-image of Y, right? Because it may not be the case. So let's see. So you are at A3. Okay. But then you can apply F3 to it to go inside B3. It may not be equal to Y. I'm not saying it is the Y, but let's see. So you are here. Okay. Uh, and now, if you apply, so here you are at, so this is F3 of A3. Okay. Now, so we have already used two facts. F4 was surjective and F5 is injective. We still have to use this result that use this assumption that F4, F2 was on. Okay, but to use that, we need to go somehow inside B2 because that is the image of F4. So, okay, let's see if we can lift this F3 of A3 to B2 somehow. So now just apply psi 3 to it. So psi 3 F3 of A3 is same as F4 phi 3 of A3, right? Okay. But then, sorry, this will be A3. But this is A4, and F4 as F4 was psi 3 of Y, right? So now you can easily see this minus this belongs to kernel of psi 3. That is same as image of psi 2. And so uh, we are almost there. So we can lift it to some small b2 under this map psi 2. Oh, so now we are here. And now just apply the fact that F2 was surjective. So this B2 will have a search, will have a pre-image. Let's just call it small a2. This is inside capital A2. So this is F2 of A2. Okay. Now we are almost here. So yeah. But again, you see, uh, so what was the goal? What was the goal? You need to find some pre-image of this Y. This is this Y. We are almost there, but not quite yet. Let's see. And now you can take, we have this F A2 inside capital A. Now you can apply phi 2 to go inside A3. Let's see if we can manage to get something from that. So this is phi 3, sorry, we need phi 2. Phi 2 of A2 will take you inside A3. Yeah. And now apply just F3. Let's see what happens. F3, phi 2 of A2. F3, phi 2 of A2. What is this? Uh, So this is this. So this square is commutative. So that is same as psi 2 f2 of a2, right? Just this equation. And this will take you to f3 of a3 minus 1. And now we are done, right? Because we have got this pre-image. So y is, if you just take y from right to left and take this f3 phi 2 of a2 from left to right, you get what you need, right? So this is a pre-image. So yeah. So we've been able to prove that if 3 is surjective. And from the first part, we proved that if 3 is injective. So now comes the main result, the most useful one. So the result says, so suppose you have two short exact sequences. You have A, B, C to Z. This is a short exact sequence. And you have A prime to B prime to C prime to Z. You have, suppose both of them are short exact sequences and you have maps between these A prime, A to A prime, B to B prime and C to C prime such that both of these squares are commutative. Then if A is isomorphic to A prime and B is then if C is isomorphic to C prime, then you have B is isomorphic to B prime. That is obvious, right? Because of these last two results. Because here this both of them are zero module. So any if you take any map, this should be both surjective and injective, right? So first apply, take this map as onto, and because both this and this, take both of them to be 1 1 to get this map. Let me just call it F. So from this you will get F is 1 1, and then just take, say, use this map. Let's call it, so let's suppose this is 1 1 then. You can take, because there is only one map, so it has to be the zero map. So it is 1 1. And use the fact that this map is surjective. This map is surjective because both of them are anyway isomorphism. So you can later on. So from there you get the fact that this F is on. So F is injective as well as surjective. So F is an isomer. F from say B to B prime is the module isomer. Of course, we are dealing with modules. Yeah. So this is sometimes useful if you have such a scenario where you have two short exact sequences and you have such nice maps such that the squares are commutative, then you don't need to check if this middle one is isomorphism or not, because suppose you have this the right one and left ones are isomorphism, then you can, using this five lemma, you can say directly that this middle one has to be an isomorphism. So that was the usage of Five Lemma. Okay, so let me just stop the video here, and from the next video I will start the snake lemma. I think I may need more than one video to complete this snake lemma research. So, just stop it.